Gathered in front of you today is San Diego State's weather engineering team with our product, the WETnet. This project consists of two teams, the software team and the hardware team. Hi, I'm Nathan, the project manager for the hardware team, and today we will be introducing our product, discussing the software used, explaining the hardware that is implemented, and concluding with our logistics. So, SDG&E found its original need for a weather sensor with its ability to predict wildfires, their spread, and the climate around utility lines. Their current system measures temperature, humidity, wind speed, and wind direction. One issue with this network is resolution. Only a couple nodes are placed in a wide area, so the measurements are an average between the two nodes. Another issue is a specialized technician is required to install these nodes. With the WETnet, anyone can easily deploy a dense network of sensors and in a low-cost package. With the WETnet, you can measure temperature, humidity, wind speed, wind direction, air quality, and UV index. The addition of these two sensors allows for researchers to get high-resolution data on the microclimates within an area of interest, as well as aid SDG&E in optimizing HVAC systems and setting up solar panels. Next is Steven, the software project manager, to discuss the overview of our system.
Hi, everyone. So in order to meet the needs of SDG&E, what we provided is a website to display our weather data, a server to collect our historical weather data, and then a weather sensing network to actually collect our weather data. Our weather sensing network has subnodes and supernodes, where subnodes have a limited sensor package and our supernodes have a fuller sensor package. How our system works is the subnodes collect their data and then they send it to the supernode. The supernode collects its data from its local sensors and then formats the data from the subnodes to be sent to the server. The server takes a single data time instance and puts it in its historical data set, and this data set is read by the website and displayed for the user. So why is our system different than what SDG&E has? It's unique in its small deployment radius and its high accuracy. This type of system, you can tell the different microclimates that would be best for deploying long-use, high-cost equipment that could, in the end, save SDG&E money. Here to talk about how our data is displayed, here's Yusuf to talk about the website.
Thank you, Stephen. So a large aspect of this entire project is actually how the website is designed and laid out. So we had a few restrictions on how we can actually implement this. One of the restrictions was that we had to have a visual representation of where each node is placed while also having the data simultaneously be displayed side by side. So the biggest reason for this is for example, if you wanted to compare multiple nodes, say one that was in the sun next to the engineering building, like node 10, and then one that was next to like arts and letters, like node 3 that was in the shade. So we wanted to be able to see simultaneously the difference between the two, like having the graph representation and everything like that. So we developed this pop-out side menu right here. And basically what this is that when it's collapsed, we have live data for everything that's available. Then when it's opened up, like it just was right here, we can have a full direct view of every single thing, compare multiple nodes and everything like that. If the user wanted to actually be able to view the entire file for the last 7 days with the data, they could download the CSV and view all that information. So I'll toss it over to Kevin, who will explain more about how the Google API and how the heat map works.
Thank you, Yusuf. So as Yusuf said, we are using a Google Maps API for our map. As you can see, we have our this acts as a visual representation for our node locations. So if you were, say, for example, to click on node 6, thank you. An info window will show up, showing you the displaying the name of the node that we have just selected. So, for example, this case, this is supernode 2, and then the data that is displayed is all the data, the sensing data that node is collecting, and what it is actually showing is an average of the data displayed throughout, indicated by the times letter in the pop-out window. And so another useful piece of information that we added in this info window is the deployment details of the of the supernode. So say or of each specific node. So say for example, this one out right here is deployed on the ledge outside the senior design lab. Now, and also we can click on another node, say for example, node 7. And as you can see, since this is a subnode, there's a lot less data being collected. And so another interesting thing that we added to this map is the heat map layer, as you can see right here. So as you can see, since the temperature of subnode 5 is actually 51 degrees, you can see that it's actually a little bit greener than if you were to say click on node 7 right here, or 9, node 9. Right there. So you can see the temperature there is actually 62 degrees, and then you can see that the heat map is actually a little bit more red in contrast. To talk more about how the slider works in the left-hand side, on the right-hand side, here is Brandon.
Good morning, everybody. My name is Brandon. So I'm going to be talking to you a little bit about the slider. So if we can pop out this menu here. So this slider is one of the most important features of our website. So this is essentially the entry point for the user to view the data that we have stored in our database. So by changing the maximum of this slider, we're actually going to say that we want to view data from this start point and this end point. And as you notice here, it's changing in 10-minute increments. And this is really important because your average weather station will typically be giving you averages, and they don't be very specific. But with our system, we are very granular, and you can see the very minor details and changes throughout the day. So if we look right here, so we're currently looking at 4:26 midnight and 4:26 at 8 a.m. And you also notice that there are some pictures here. Well, you see, our supernode is actually node 6. And so these two pictures are real pictures that we've taken on deployment. So, and this left image here correlates to the start time, and this image on the right correlates to the end time that we selected. And along with that, if you just scroll down a little bit, you can see the graph that's also showing, kind of mirroring the data in a way. So it's really cool that we can visualize with the pictures as well as the graph how the temperature is changing there. So if we just scroll so that we can see kind of the graph and the images at the same time, you can see there. So we started at midnight, right? So it's going to be a little cooler. The sun's not out, so it's hovering around 45 degrees. But then as the sun starts to peek out and come out, you'll see the temperature just rise up there and kind of match what the image that you're seeing there. So that's one of the really cool, unique features of our weather station because, again, like with a typical weather website, they'll be interpolating data and giving you averages. But with our website, we're actually giving you raw data, and we're giving you those exact readings every 10 minutes. So if you just scroll up here and click again on the last 7 days, so that current view we just looked at was the today view. So that allows the user to select the time frame from the last 24 hours. But with this last 7 days feature, we're allowing the user to see the last 7 days to have a more full range to view data. So now, again, you can see those images correlating to the start and end times. And if we scroll down, you can kind of see those different peaks and valleys that are happening throughout the course of the few days there. So again, this is just really interesting to see all of these very specific readings that are coming in because you normally don't get that fine detail from a typical weather station. So to kind of explain and go into more detail about how this graph actually works, I'll hand it over to Philip here.
Since data analysis is sort of the main point of our project, we had to put all of this data in a way that's very easily presentable to the user and in a way that's very easy for them to compare the different values between nodes and see how the temperature and shade correlate. So as you can see right here, you can check between the nodes by adding them with this node selector and the compare button right here. So you can have multiple nodes on the graphs at the same time and check their deployment details against how the values change. Additionally, you can change data right here with these radio buttons, so you can view temperature, humidity, and all the sensors that we have. We also made this user-friendly by removing any data that's not on the subnodes by removing them from the actual website being selectable. So if you go to, say, node 6, you can see these extra options such as air pressure, wind speed, and wind gust. And lastly, if you click wind direction and air quality index, you can actually see values at the bottom that take the averages of both supernodes, and you'll be able to see what those values are in the area. Here to talk about how the data actually comes into this network is Brent.
Morning. For the network, what we have is a very easy setup, as mentioned earlier. What this means is as soon as the system is powered up, we'll automatically connect to whatever Wi-Fi is currently available. What this will do is allow for easy maintenance, as any user or maintainer can go ahead and log into the Pi's and actually be able to tell what the current status is and whether they're collecting from the subnodes. And so what this can do is give a instant recovery if there's ever an issue where it can't be connected to. All it needs is a simple restart, and it will reestablish this connection. It also keeps it very synchronized because we're able to use local NTP servers to keep the timing on campus, as well as updating the time with each subnode so that all the data is collected in its very specific time slot, and gives it a very strong ability to not phase over time to different time periods. This also allows for remote maintenance over the internet, as any maintainer can go over the internet and through Volta log into the specific node that they either want to update or they want to change for the time being. And now with the actual data collection, we have Ankin.
All right, now I'd like to talk about the data collection and formatting. So we have the subnode right here, and the subnode has the sensors, for example, temperature, humidity, and UV index. So what's that going to do? It's going to basically send to the radio protocol, and then it will be going to the microcontroller and be sending to the supernode. And the supernode itself also has its own sensor, as mentioned before. It's got such as the wind pressure and wind gust and so forth. And now you have all these data, the local data and from the subnode. And what is it going to do? It's going to go through the Raspberry Pi, which is like a mini computer, and it's going to go through a supernode class and a subnode class. And it's going to differentiate the both the two and, of course, organize it and consolidate the data. And this will be stored in a library and in a JSON format. JSON is a JavaScript object notation, and it is useful for a project, especially because it's compatible for many languages, and especially we are using Python and JavaScript and all the other languages. And on top of that, we have a list of objects and list of data, and that's perfect for JSON. Now, up next about how the subnode is communicating to supernode will be Ben.
Morning, everybody. So for our application, we've gone with the XBS2C radio, which uses the Zigbee protocol. For our communication protocol, we've tried to make it as simple to set up and easy to use as possible. So we're using dynamic node assignment. So essentially what happens is turn on supernode, it immediately starts sending out pairing messages. As you turn on each subnode, it'll respond to that pairing message with its own node number, which will be assigned to itself. That will correspond to a time slot or a bin where it is to send its data periodically over the course of the total period. We're also using a feedback control message to use as receipt of confirmation and to adjust the timing to account for oscillator drift and to help avoid collisions between subnodes and supernodes over the course of the deployment. And to talk about the deployment, Joe.
Awesome. So a great feature of our system is the fact that it's simple and easy to use or to deploy for any users without any technical background. Basically using a single board computer known as the Raspberry Pi, we basically collect data via the sensors that we use in the subnodes and send it to the server. Once we have the Raspberry Pi turned on, we can log on and connecting it to a monitor to then start up the program. Our program basically initializes the pairing between subnode and supernode via Zigbee. Once they're paired, we then deploy them out into the field. However, when we deploy them out to the field, our subnodes are very sensitive because they do have UV sensors, temperature sensors, and humidity sensors. So when we deploy our subnodes, we want to put them in areas with little or no obstruction. So you don't want to place them in an area where there's a lot of shade that can affect the data we have. Also, for a supernode that will contain the anemometer and wind vane, which we talked about the hardware, which we talked about by the hardware team, well, we want them to be placed on a position where we can collect enough data and accurate data for the supernode. One great feature, as Brent said, is the maintenance portion of it, is the fact that we have 8 subnodes that we will deploy out into the field. However, to make it easy without having to be on site, we can access the error log via Wi-Fi to determine which subnode isn't currently working. And that saves us time and effort to actually go out there and check each individual subnodes that we have deployed. Since our Zigbee S2C has about a line of sight of about 120 meters or 400 feet, we want to make sure that we're within that range when we deploy our system. As you can see in the next slide right here, Our current supernode is deployed on top of the engineering building, while we have a subnode using Velcro on top of a light post. So now that we've talked about the website, as well as the connection and communication via Zigbee, as well as deployment, here is the hardware team to talk more about the sensors and devices that we use to collect the data. And first off is Johnny to talk about the PCB layout and supernode diagram.
How's it going, everybody? I'm going to try to bridge, my name's Johnny, I'm going to try to bridge the gap here between software and hardware. So as previously mentioned, we're using a nodal relationship, a supernode, which is kind of the mother hub, and a subnode acting as a supporting cast. So presented here, we have the supernode block diagram, and as you can see, we iterated before, we have 5 sensors: the air quality, wind direction, wind speed, temperature, and UV index. Also attached, we have the mini computer known as a Raspberry Pi, the camera attached for vision, a Zigbee radio for communication, and a PIC24 microcontroller to process all of the logic. The supernode will run off 3 volts and 5 volts respectively, powered from the Raspberry Pi. It will then collect data locally and periodically, pushing it to our JSON server and then forward it to our website. Next slide, please. So a huge challenge in this project was realizing our design from inception all the way to implementation. I can speak for many students like myself. You're in class, you're crunching out circuit theory, you're looking at voltages, voltage dividers, even transfer functions, current calculations, whatever it may be, and you don't quite get a feel for it. It's on paper, and the next step from the university's curriculum is to go into the laboratory, kind of breadboard out the solution, probe it, check the current voltage, and that's still not the industry standard. The printed circuit board gets us to that destination. So we had to create 2 custom boards to meet our mobility requirement. Using software, routing techniques, spacing proximity, we were able to create 2 custom boards and deploy safely into the environment. If you go to the next slide, these are some of the finished products we have of the supernode. These are the sensors that I mentioned before, as well as the support circuitry on the right, and then one more. And we can see the subnode here, which is a little bit smaller, compact design that needs to be easily more manufactured all around campus. So once these boards were printed, the next step was to create custom enclosures. Especially here in San Diego, we have horrible weather conditions, so we needed to make sure it would take on all the conditions that it offers. So to talk more about the enclosure design, I'm going to hand it off to Noel, and he's going to go further into detail.
So as Johnny was saying, our design isn't as complicated, so we didn't need to make our custom boxes 3D printed because of time and effort. So we chose to buy our Hammond enclosures, and that gave our design to be cost efficient, mobile, and discrete. Since, as you're looking right now, is the supernode, and this will be actually mounted on either on a tripod onto the engineering building, as Joe would say, and onto the subnode, next slide. And this will be also bought from Hammond enclosures to offer also compact mobility and to be discrete, because we do not want any other personnel other than ourselves to be debugging this on top of light poles. And now to talk about one of the sensors on the supernode is Alvin.
Hi everyone, my name is Alvin. I'll be talking about the air quality sensor. The sensor that we used was the TGS2600. What it does is it takes in the pollutants conductance and it outputs a voltage depending on the amount of pollutants in the air. What we wanted to do was calibrate the sensor driver to the AQI index levels around San Diego so that we can get an accurate reading, because it only outputs the voltage, it doesn't really output a level. So what I did was I went to Del Mar and El Cajon to calibrate the output voltages. On the next slide, you can see the data that we collected from testing. From Del Mar, which had an AQI level that was considered to be good, we got a 0.27 volt output, and at El Cajon we had a 0.38 volt output for moderate. So you can see that the sensor works. So the higher pollution there is in the air, the higher the voltage output. Some other interesting pieces of data that we collected was in the senior design lab when it was empty sometime during spring break. I tested the air quality, and the output was about a 0.17. But when it was full of students working on the projects, the output was 0.56, which is very high. Also, the freeway, I tested the air quality by A lot, which is by the freeway down, so in the parking lots in the freeway. The output voltage was 0.78, which is a very high moderate. Yeah, so it's probably not good to drive if you're
top down on the freeway. Convertible. Next to talk about the wind direction, how we get that is Matthew.
Thanks, Alvin. So for the wind vane, we chose the sensor AS5048B, which is a magnetic angular rotary sensor. So we chose the sensor for one, the I2C hexadecimal values that are being outputted range 360 degrees, which allowed us to correlate 8 hexadecimal values with 8 of the compass directions. Another reason why we chose this sensor was it's known to be susceptible to a wide temperature range and is used consistently in outdoor and industrial environments, which is necessary for our project because the sensors are constantly exposed to various weather conditions. For the body of the wind vane, we have 2 bearings to the top and bottom. This is just to increase stability and fluidity of the wind vane as it rotates. And the magnet is attached to the inner shaft of the wind vane and it's just above the sensor. And over a 10-minute period of time, the common direction is outputted. Now to talk about the anemometer is Jeremy.
So what we have here for the supernode is the anemometer, or a wind speed sensor. And the way it works is that there are 3 cups on this anemometer, and each time a cup catches the wind, it begins to spin. And when it spins, it rotates the inner shaft. And at the bottom of the inner shaft is a permanent magnet. And at the base of this anemometer is a Hall effect sensor, which detects changes in magnetic fields. So as this magnet rotates and it passes that Hall effect sensor, it outputs a pulse. And from that pulse, we can correlate that to rotations per minute, and from there to miles per hour of the wind speed. Now that you've seen all of the unique sensors on the supernode, we'd like to introduce you to our subnodes with a block diagram by Lee.
This block diagram of the subnode. The battery we use is for lithium battery, which is connected to the voltage regulator to produce 3.3 watt voltage supply. And we're able to measure the temperature and humidity and the UV index for our subnode system. Basically, how the subnode system functions is the microcontroller of the subnode receives the data from those 2 sensors by using the I2C protocol, and then send it to the microcontroller of the supernode by the ZigBee, which is a radio transceiver. For more information about the hardware, discuss to
next week. So after knowing the generic design of our subnodes, let's know about more specific features of our subnodes. So for our subnodes, it's accurate, low consumption, and low cost. So for each subnode, it takes only about $65, which enable us to build more subnodes we can put on different locations on campus to collect more data we need. And for these 2 graphs, gonna show the accuracy of our data. The graph 1 gonna show us about the UV sensor, and the graph 2 is about the temperature. And we compare the data with the online data, and also compare the temperature data with the thermometers, and we can see that 2 lines are kind of touch each other. It shows the accuracy of our data. And for the next slides, we can see the power consumption of each components are really low. And for we measure it as we set it wake up every 10 minutes, and we can see the standby current and active current for each component, and we multiply the times, and we can see the total consumption going to be 0.7 milliamp hour, and we use 380 milliamp hour batteries, which can let our subnode work more than 20 days. So let's hand over to Mason to talk about the brain of our subnode.
So the PIC24 is the brains of our subnode. Since it is battery powered, we wanted to use a low power RC oscillator as the clock source, which collects data from the sensors over the I2C bus every 10 minutes, and then it sends that data to the ZigBee over UART, so it can be sent to the subnode, or the supernode. Then, to monitor the charge of the battery, voltage from the battery is fed from a voltage divider into an analog to digital converter, which will send a message when the battery voltage gets too low, which ensures that the battery never gets discharged to a point where permanent damage can happen to the battery. Another perk of using this is if a subnode happens to go offline, we can instantly check to see if it's just a battery problem or a more serious problem has occurred, and then that really helps with troubleshooting. Next, to talk about how we spent the money SDG&A gave to us
So I know what everyone in this room is thinking right now. How much does this amazing project cost, and can I have one? So with one easy payment of $1,200, you can have one. No more sleepless nights wondering what Mrs. Johnson's turtle pond's UV index was. You'll know. As you see, most of our money is spent through sensors, cameras, and radios, also for testing. The rest were used for miscellaneous battery powers, and the price of a supernode, as you can see, is about $200, and the price of a subnode is about $70. So with this project, we had many milestones that we set out to accomplish in the beginning. Shown in green are the ones that we successfully completed on time, while the red took longer than normal. Such as, it took longer than normal for prototyping the subnode and the supernode due to learning like Mentor graphics and how making each device, you have to make the partitions, the cells, combine them, and you have to connect them correctly in the schematic and then route it. So it may sound easy at first, but eventually when you do it, you figure out it's not really easy. And after deploying it, there may still be problems. But all in all, you learn a lot, and it's a learning process, and you'll get smarter every day. For closing statements, here's Jeremy.
Nice weather we're having. We'd like to thank our sponsors, SDG&E, for giving us the opportunity to work on this project and for showering us with advice along the way. You know how the old saying goes, April showers bring May flowers. Well, in April, we showered this project with our blood, sweat, and tears. And in May, it's coming to fruition in front of you. We'd also like to give a special thanks to John Candy and Mark Bruno for being the sunshines on our cloudy days. Now, if you don't mind, I just saw on node 7 that the temperature was 75 degrees, the humidity was 25%, and the UV index was 6.
Thank you.